Ladies and gentlemen, honored Composite United members, welcome to another episode of our new online educational series, See You Online, See You Prepared for Future. My name is Bastian Brenken and I will lead you through today's episode. Today's topic is additive manufacturing of composite tooling, and it's a topic that I dealt with during my PhD. So I will present you my PhD work today. When you think about additive manufacturing, usually you think about printing prototypes, printing parts directly, but the topic of printing composite tooling is generally what I can see oftentimes overlooked, and the potential is not really in people's minds. So what I would like to you today is to put this potential, to make this aware to you, and this is the goal of today's webinar. That's the outline for today. I will give you a little bit background at the beginning, talk about the fused deposition modeling process, which you're most probably aware of, and then I will go into an extension of this process, the extrusion deposition additive manufacturing process. Also, I will explain the general traditional tool manufacturing. After that, I will go into the manufacturing steps of how to make a composite tool by additive manufacturing. So I will lead you through the tool manufacturing process, and at the end I will give you some examples of printed tools. And then I want to dive into accelerated development through simulation. Simulation is an important part of it, because otherwise 3D printing, or also extrusion deposition additive manufacturing in this case, is only trial and error. And if you think about large scale tooling, there's lots of material that you can waste if you don't know how to do it right. So I will introduce some modeling capabilities that were developed in Abaqus and how these capabilities can be used to predict the outcome of a print. At the end, I will conclude my talks with the main takeaways. I want to point out that in my current role at Composites United, I'm not working on this topic anymore. This work was performed during my PhD at the Composites Manufacturing and Simulation Center at Purdue University in the US, in the United States. So if you have questions about this, of course I'm still in contact with my former research group. Then you can write me an email. You will find my email address at the end of this presentation. Let's start with the background. So the fused deposition modeling process, or in short FDM process, is a prototyping technology that was invented by Stratasys in the early 90s of the last century. So the typical extruded diameters, you have 0.1 to 0.3 millimeters, and you can see the process on the right. So you have a nozzle that's depositing a hot molten material onto a printing bed. And by depositing this material, you can build up a 3D part layer by layer. Typical materials that are used are PLA or ABS, or also high temperature materials like PEI. And the advantages of this process are that you have a toolless production of intricate parts, so you don't need any support. You can define. You don't necessarily need support. You can, for overhang, there can be support material that is required, but you don't need tools. You can build up the part just by putting the layers on top of each other. You have a significant rate reduction with this process. That's possible by using partly filled layers. You don't need to fill up every layer completely. And it's very easily scalable, and you will see what I mean by that in a few slides. The disadvantages are, or challenges are, that you have that the strength, especially in the stacking direction, can be really weak, because you need to make sure that the next layer, or the deposited material adheres well to the formerly deposited material. So the material needs to fuse, the polymer chains needs to diffuse into each other to have a good bond. And if that's not the case, if the former the previously deposited layer is already too cold, then this does not happen, and you get really weak strength. And you always have an anisotropy, and this anisotropy, it's very dependent on the stacking sequence, the layer and the setup of the layers, the directions. Now let's talk about the extrusion deposition additive manufacturing process, which is basically an extension to a larger scale. So you aim at larger parts, and a consequence that you need for that is that you have to have a higher material deposition rate. You typically use pelletized material as feedstock and not filament material, which makes this the raw material cost, which reduces the raw material cost. And fiber reinforced material helps to suppress warpage. And on the right in these videos, you can see the visual image and the thermal image of a buildup where hot molten material is added, and the part is built up layer by layer. Typically also compaction device is used, and in the thermal video there was a vibrating plate. I can just start the video one more time. You can see here a vibrating plate, and you need that because your bead diameter, so the diameter of your deposited extruded material, if it becomes larger and you put the beads next to each other, then you get voids in between because the material does not fill up the whole volume. Because if you take a circular bead cross section next to another circular, you get voids in between. So a compaction device helps you to push down the material and to compact and to fill these voids. If you use fiber reinforced materials, composite materials, then as a result of the printing process and the physics in the process, most of the fibers align parallel to the printing direction, the one direction in the diagram on the right. So the consequence is that if you look at a cross section of this extruded material, you see mostly fiber circles and ellipses, because most fibers are oriented in the printing direction. As a result, you get a very anisotropic part behavior, and it's already anisotropic using unfilled materials, as I explained before while going over the FDM process. Now you have this anisotropy already on the level of the extruded material, so on the level of this bead that you see on the right. And as a consequence, you have an anisotropic mechanical, thermal, and also the flow properties. The behavior and also the flow properties are anisotropic. The advantages of using fiber reinforced materials are that you have improved mechanical properties, but more important than those for the application of tooling is that you have a reduced part shrinkage. If you look at very large parts, only by part shrinkage a printing process could be interrupted, and you would not be able to conclude the print. So by adding fiber reinforced materials, short carbon fibers for instance, you can suppress this warpage, and you then can conclude the print. Another an interesting aspect is that by adding short carbon fibers, you can control the coefficients of thermal expansion of your tool, because as you can imagine, if most carbon fibers align parallel to the printing direction, the consequence is that your CTE in this direction is very low. So at least layer-wise, how you orient the layers, you can control how your tool is going to expand in a later heating cycle. Let's talk about some of the technology that was developed. So typically, if you think about 3D printing, you think about a small desktop printer, but the extrusion deposition additive manufacturing process looks at a whole different scale, and this is shown here. So on the left, you have the large scale additive manufacturing, or short LSAM system, developed by Thermwood, and you can see this big machine in the picture. the build volume can extend up to 30 times 3 times 1.5 meters. So you can print huge parts with this machine. What's very special about it is that you have two gantries that you can see. On one you have a single screw extruder mounted vertically, and you print with this gantry. On the second you have a CNC mill. So without having to change the position, you can first print the material and then machine it down to size. And the machining step is required because for a tool and also for many other parts, you want to have smooth surfaces in the end. And if you deposit lots of material with a large bead diameter, the surface roughness of the walls becomes significant. So you need smooth, flat surfaces with a low roughness. So for that, you need to machine after the print. On the right, you have the Big Area Additive Manufacturing System, or in short BAM system, developed by Cincinnati and Oak Ridge National Laboratory. And their build volume can also be very, very big compared to the standard FDM printers that you're used to. As large part in my first part of this talk, I want to talk about traditional tool manufacturing, and I want to make you aware that it's a lengthy multi-step process. So first you need to set up a foam block, then you need to machine this foam block and seal the foam to get the tooling master. For that you need to lay up the composite material, cure it on the foam block, and post-cure it. Take it out, and then finally you need to mount the finished tool surface on a support structure. So additive manufacturing here has the potential to significantly speed up this tool manufacturing process, and how this is done, that's what I will talk about now. So as an example part, I will talk about this, or I will show this air inlet duct that you see there, which is typically used on airplanes and cars to cool the engine or to let in air into your structure and the internal parts. And originally we had this tool available in the lab at Purdue University, made from metal, that you see in the bottom left corner. And it was just an aluminum tool, and we wanted to see, but it was an autoclave tool. So we wanted to see, hey, can we print this, and can we actually have a printed tool that is capable of producing parts in the autoclave? These are then the steps that you need to go through to get to a printed part. So first you start with your CAD geometry that you can design in any CAD program available, for instance, CATIA. Then you have to slice this geometry and transform your continuous geometry to a discrete sliced geometry in the slicing process, where you define your layer setup. Then, as a consequence, you get machine code out of the slicing process that you can then feed into your printer, and your printer will follow this machine code and print your part. And as a last step then, to get smooth surfaces, as I just explained already, you need to machine this tool. And a coating in the end is optional based on your preferences. A coat of course extends the tool life, etc. So let's go through these steps, and I will talk about them a little bit more in detail now. So for the CAD geometry, you actually need two geometries. You need the print geometry that describes the shape and the dimension of the printed geometry, and you need your final geometry that defines the final tool shape and the final tool dimensions. And the reason is obvious, because you need to machine down to the near net shape at the end. So you print near net shape, and then you machine down to the final shape. Then the slicing process, the slicing process is the next step. You have many parameters that define your layer setup. Printing parameters, for instance, your machine, what's the dimension of your extruded bead that you have, how fine can you go with these layers that you can print. And then you have process parameters, printing temperature, print bed temperature, extrusion conditions, and constraints, maximum layer time, and the shortest layer time possible before you get sagging, before the material sags, because it's not stiff enough and not cooled enough, and a max overhang. So when do you need support material? So these are constraints, and you all need to feed these parameters all into your slicing program, and your program will then transform the continuous geometry that you have here and will create a discrete geometry for printing. As an output, you get the machine code that you can then feed into your machine. Then you have the printing process. So here, you will see a video that will start shortly. So here you see the print of this NACA air inlet duct tool that we are talking about here. So on the left you have the live image, on the right you have the thermal image, and it's important that this is a well-controlled process. So the thermal image here gives you process control, and at the same time you can validate simulations with the thermal image. After having received the printed part, and at the conclusion of the printing process, you have the machining. So again, you use your print geometry, you take your final geometry, the dimensions, and then you put your printed part in a CNC mill, and then you machine down to the final shape, to the net shape that you want. And of course you need to define machining parameters here again, that for a skilled technician, that's not a big deal. And then at the end, on the upper right, you see the final tool that we just talked about, and you also can see a part that was created with this tool in the autoclave. So using high temperature materials, like for instance the material used here, the 50 weight, the PPS material reinforced with 50% carbon fibers by weight, you can definitely print high temperature tools like autoclave tools. And then at Purdue we wanted to see how far can you actually take it, and we tried to print tools for different high temperature applications. For instance, thermoforming. On the bottom right you see a printed half hemisphere tool. This is a two-sided tool, so it has a female and a male part. And then we heated up this sheet of discontinuous carbon fiber material, and we put it in, and we were able to mold it at higher pressures than autoclave pressures. And then we went even another step further and wanted to see, can we do compression molding? And you see on the lower left you can see the compression molding tool for a pin bracket that was also shown. So even compression molding with processed pressures of up to 30 bars roughly, we were able to do, and we were able to use printed tools for that. Of course, these tools then don't last forever. It's still a thermoplastic material. This material still creeps when you heat it up and apply a big pressure. So just to give you an idea, an example, the printed compression molding tool there lasted for about 10 cycles and then it broke. But for prototyping or for very small number series production, or for a tool during the tool development phase, so that's still a huge potential that you can see there in printing tools. Of course, there are also high temperature tools that you can print with the traditional FDM technique. So Stratasys, as the developer of this technology, has explored this a lot. And they typically, for high temperature material tools, they use Ultem 1010, but unreinforced. So it's an unreinforced PEI. And example tools, and with produced parts on these tools, you can see on the right. And on the lower left, there's also a very interesting concept. They have sacrificial tools. So you can see this tool on the left here that was built up, and then you put a layup around it and you cure it in an oven. You get your part, and then it's soluble, the core. So you can remove the core, sacrifices, and get this hollow part in a very easy way without having to machine and build a very complicated tool for that. So it's a very neat application. There's lots of potential for tools, as I've said, and this is a good example for that. Here I want to show you a large-scale example. This is the LSAM system in action. So, and what's being printed here, it's a helicopter blade tool. So a very big tool. This is approximately 6 meters in length. So it's a whole different dimension than the NACA duct, air inlet duct tool that I've shown you before. Here, the material that was utilized is carbon fiber reinforced PESU, which is amorphous, and thus it does not shrink as much during the printing process as the semi-crystalline PPS. Now we switch to the time lapse. You can see the build-up. It takes several hours, but still it's much faster to print near net shape and machine to get a final tool than to do it the traditional way that I explained to you before. So now the print is finished, and now in the same build envelope we can use the CNC mill, the gantry with the CNC mill, and machine the tool down to the final net shape that we want. Put it on the side, machine the actual surface of the blade. You can see this done here. A more detailed view on an edge. And this is the software that is also sold by Thermwood for the design, the slicer software. And then based on the compaction that you have, the vacuum testing works. It holds the vacuum steady, and you get a tool in a very short time. These are other examples of large-scale tools. On the lower left, you can see a trimming tool printed with the BAM printer, with the other large-scale printer. And for a certain time, it was the largest tool ever made in one piece. You can see here an official from the Guinness World Records committee measuring the tool for the world record. And on the right, you can see a wind turbine blade tool printed with the BAM system, but in many segments that were put together. But still, you get a big tool in a short amount of time. So now I want to dive into the simulation part of it. And to be able to simulate the printing process, you need basically a new architecture. You need new functionalities. And in Abaqus 2017, these functionalities were introduced, because during a print, material is continuously added. The domain of your part is continuously changing. So you need to activate elements to depict the printing process correctly. And how Abaqus has done this is that you have to define in the first step an inactive part, unspecific mesh. And then Abaqus utilizes the same machine code that you need for the actual print, and it runs the machine code through the mesh and activates with the definition of a certain cross section of your extruded material. It activates the elements on the fly. And then the physics computations are for activated elements only, which keeps the simulation quite inexpensive compared to the fact if you had to compute the physics for all elements for each increment. The physics, the description of physics can then be done with built-in tools or custom-made user subroutines. At Purdue University, we utilize this functionality, this novel functionality. By the way, it's built in from Abaqus 2017 and on. So in each version from Abaqus 2017, you have this capability that comes free of charge if you have Abaqus anyway. And from Abaqus 2018, it's also built in the GUI. So the graphical user interface. At Purdue University, we utilize this, as I said, and we build a sequentially coupled development tool, basically. The first two steps of simulation are very identical to the physical printing process. So you start with the geometry, you get the print geometry, and then do the slicing process to get the machine code. And this machine code is then fed into two sequentially coupled analysis. First, we have a heat transfer analysis to compute the temperature field throughout the process, to compute how the material cools down. And these transient results, along with the machine code as well, are then fed into a second analysis where you compute crystallization behavior of a semi-crystalline polymer if you have one, and also mechanical, you do the mechanical analysis. So you look at stresses and deformations. And this set of simulations is then a part design tool, what I already said. So you can have then iterations. Let's assume you want to design a certain tool, and you have characterized the material, and then you can go ahead and try a certain print setup, a certain machine code, a certain structure of your tool by just running the simulations and then looking at the distortion and the internal stresses and then see, is this acceptable? Is the shrinkage of my part, the anisotropic distortion, is that acceptable? If yes, fine, you can go ahead and machine it to get to the final shape. If not, you can redo this virtually, and you don't have to spend these big amounts of material as we've seen for the big scale parts and tools. You can just do it virtually. So this is a very neat thing, and in our opinion was very essential to making this a real option to produce tools. Here's then the simulation. On the left you can see the temperature, and on the right you can see the deformation. So the elements are activated at the extrusion temperature and then cool down. And on the right, the tool is first attached to the printing bed, so the deformation is really low. But after conclusion of the deposition process, you can see the tool being disconnected from the printing bed, and then it's approaching its final deformation state. And you can see here a magnitude of whole deformation magnitude of 0.6 millimeters. That's not very, very big. If you imagine that the tool itself has a length of roughly 15 centimeters and a width of, let's say, 7 centimeters, 6 to 7 centimeters. So 0.6 millimeters seems fine considering the machining step that's still required after the printing. But if you think about bigger tools and a helicopter blade tool, then these magnitudes can turn out to be very, very much larger, and they can be very, very significant. So simulation is an essential part of the whole thing. This is also shown by this tool case study. So what we did, we took this part, the CAD geometry, and defined two infill patterns, two printing patterns. One with sparse infill, where not each layer is completely filled, and another one with solid infill on the right. And then we did the simulation, the sequentially coupled simulation, and on the left you can see a very different final deformation state than on the right. And here we are looking at the U3 deformation, so at the deformation in the Z direction. And it's interesting to note certain behavior on the left. Your maximum orientation of the curvature follows somewhat this infill, which makes sense. So we have a very, very similar angle here, and on the right, it's not perfectly symmetric, but it's pretty symmetric compared to the left with the solid infill. So it kind of makes sense how the material behaves. But this gives you a good impression of how you can use the simulation as a design tool to design your tool before you actually print it. So in conclusion, extrusion deposition additive manufacturing with fiber reinforced polymers was adopted by many companies, and you saw the large scale printers that were developed, which are a whole different thing than the desktop printers that exist for 20 years. Mid and large scale composite tooling was printed, and parts were taken from it and manufactured from them, both for low and high temperature applications. In addition to the machine technology, simulations were developed, and these simulations can act as a design tool and they can enable a virtual tool development before the actual print. So they are coming really handy and are especially valuable if you look at large scale tools and lots of material that needs to put down that you can save by doing a virtual analysis first. So I think in conclusion, these combined capabilities allow a significantly faster tool development, and they are especially as interesting for very small number serious parts where the tool costs make up a significant amount of the total part cost. So for that, with this, because you can really go in the tool developments from months until you have a tool ready to days until you have a tool ready by just printing your net shape and then machining. So based on that, you can save a significant amount of cost, and as a result, low serious composite parts, low volume composite parts may become feasible based on this technology. So I think AM for composite tooling is a major disruptor of the traditional market for composite tooling. So what's next? You're wondering, okay, these large-scale printers looks nice, but it's probably a significant investment. And the answer is yes, it is. And also running the simulations the right way, considering the anisotropic material physics the right way and implementing them into the simulations, for that you need know-how and experience. However, usable tools can already be printed with the small FDM printers. I've shown you some professional tools made on Stratasys printers, but even with your desktop printer, for low temperature applications, or think about trimming tools for small parts, you can just go ahead, try to 3D print them. And my advice is do that, try and learn, because I think the potential is significant. And you should definitely keep additive manufacturing in mind for producing and manufacturing tools. With that, I'm at the end of my presentation. I want to thank you for your attention, for your interest in participating today and watching this. And if you have questions, feel free to shoot me an email. It's the first email, bastian.brenken@composites-united.com. And also, we'd like your feedback on this video. Did you like it? What can we improve in the future? So please send us your feedback. That's my colleague's email, katerina.lechler@composites-united.com. Thank you very much, and bye-bye. Have a good day.